Hello. Leetcode 35 search insert position. Let's get into it. So you're given a sorted array of distinct integers and a target value, and you need to return the index if that target is found. If it is not, return the index where it would be if it was inserted in order. So just reading this, you're given an array, you're given a target value, and you're looking at indexes. In your mind, you should automatically think some type of binary search, right? That's where we want to be when doing Leetcodes like this. And you just need to know the type of algorithm that's in the back, but we'll get into it. And the requirement that we have is writing an algorithm with O log of n runtime complexity, which also, if you're if you have like decent enough understanding, you should also know that binary search does consist of an O log of n runtime complexity, which is just another indicator or a secret hint that we're going to be using something like that. So these are the examples. So for example, we have numbers. This is what we're given, the array of distinct integers, and this is our target value, right? So we basically need to return the index that the target value is at if it is present in this, which we know the target of 5 is present in numbers, right? So we're returning 2. Why are we returning 2? Even if you count 1, 2, 3, right? But the answer is 2. Why is that? Because we're dealing with indices, right? And if you're familiar with indices, for a list, right? You're given a list. So you have 1, 2, 3, 4, right? This is your list. Your indices or your indexes, would be 0, 1, 2, 3. Arrays, lists, these things start from 0, right? So every indice that you have is pushed down by 1. If you're counting what position it is at, right? That's dealing with length. But for this, we want indices. So for target of 5, we were starting 0, 1, 2, which is the output 2. That's the indice of the target because it is present. For this one, we have target of 2, right? But it's not present. But if it's not present in the given array, we have to return the index of where it would be if it was sorted. Now keep in mind, it's giving a sorted array. So that means everything is from least to greatest, which means the entire list is increasing, which makes this much more easier, just an easier question overall if it wasn't, right? So now we're dealing with sorted arrays. That is a very crucial factor of this as well. So that means that so we look at this, right? From left to right, we need to put in 2 somewhere. Where would you put in 2? Numerically, it would be between 1 and 3, right? So you would have it over here. Now, why is this output 1? Why is this the index of where it'd be 1? Because you have 0 and you have 2. So when you have this 1, 3, 5, 6, 1, 3, 5, 6, this is what you're given, but you need to add in 2. So your new list would become 1, 2, 3, it's hard to draw on this, 5, 6. So you have 0, 1. 2 is at indice 1, which is your output in this, right? So I hope you guys understand the gist of that. But when we're looking at patterns in Leetcode or just in DSA in general, it's a lot of it's pattern recognition, right? So for this one, the recognition would be a binary search algorithm. So if we come over and start coding here, how binary search works, it works with 2 pointers, right? So we're given for O log of n runtime complexity, this is the most optimal solution. So this is how we'd want to solve. So I for now, because we're going to be dealing with 2 pointers. So if you're not familiar with the 2-pointer method, it'd be really nice to go over it. But how it works is you have so there's different ways to do it, but the ideal solution for this would be a start and end. We'll say L and we'll say R, right? So what we're going to be doing is for that target value, which we call X, right? For example, we set X equal to 2.5, which they didn't say that it would be whole numbers, right? For the constraints, there's no decimals given, so we're assuming it's all whole numbers, right? But for the purposes of this example, I'll do in a 2.5, right? So basically, what you're going to be doing is the right will be moving inwards and the left will be moving outwards, and they'll meet in the middle at some point. And that middle will depend. That middle will be the midpoint, right? So the target is going to be the midpoint. Equals midpoint. And basically what you'll be doing is you'll be moving these towards the middle or towards the midpoint until you get it. So for example, you look at the starting indice for L and you look at the final indice for R, right? Both of these are not it. So you move them inwards. So now you're looking at 1 for L, that is not 2.5, move it again. You're looking at 4 for R, that is not it. You move it again, right? Now you have 2 and 3. So 2 is not 2.5 for L, and 3 is not 2.5 for R. But if you move both of them inwards, L and R meet each other, but they also don't meet the midpoint. That means this is the indice that you return. Okay? Remember that. It's like you want to find a midpoint which isn't present. That means it's not in the given array. So that midpoint, this indice is what you're going to return if it is not present. If it is present, you'll simply just return in this order. You just start from 0 and you return. But if it is not present, you're now going to return the midpoint of where it should have been. Okay? So what you'll return now is this left indice. Okay? And let me show you why. Because if you have a list, say you have 1, 3, my 3s are bad, 3, 5, 6, right? And you want to put in 2, right? So you put in 2, you get 1, 2, 3, 5, 6, okay? So you have indice, try to change the color, okay. So you have indice 0, indice 1, indice 2, and indice 3. Now you have 0, 1, 2, 3, 4. So what search insert position is, that if the target is not found, you basically insert it and move the rest of the array to the left, or sorry, to the right. But that means you'll insert it on the left, right? So you move it in as it is. So if you think about it, your final value should return, everything should return L, right? That if nothing is found, it should return L, whether it's found or whether it's not. Because what this is you're putting it in here, X. You're putting in here X, and all of this becomes all of this. It's moved to the right. But if you're moving something to the right, you're technically putting it in at the left, right? You're putting it in at the left because you're smushing it on the left part, which is moving things to the right. It's like a sofa. Imagine the cracks in a sofa. You put your foot, put your hand, put your butt, whatever you want, into the left side of a sofa, and it'll move the right side of the sofa to the right. It'll create a new array which moves along, right? This is search insert position. You're inserting it at a position which keeps the order of the whole array. The whole array stays sorted. This is also still a sorted valid array. But now we just have our target value inserted inside of it. So now if we run back and run the whole loop, you get 0, 1. It'll return 1. That's what a goal is here. So first we need to establish the pointer. So you could say L for left, we could say 0, and you could say R for right. And this will be length of whatever we're given, which is nums, minus 1, right? And so we'll have a while loop for this, which would be while L is less than or equal to R, right? So what this means is that while left is less than R, that means while left is still searching inwards and while R is still coming this way, that means this whole thing is still looking for a value, right? That means while this is true, we'll have a midpoint. This midpoint will be the target value found, like if present in the given array or not present in the given array. We will still have a midpoint, right? So we want to determine what that midpoint is. Now, if you guys know from algebra or geometry or any of these introductory classes, right? Midpoint is basically this whole thing divided by 2. It's basically the average of the whole array. But we're not going to look at it in that sense, but that's the easiest way to say it. It's just formula-wise, that's what we have, right? So the midpoint formula, it might be good to memorize this as well, but it'll be this. This is the formula for midpoint, right? This is what gets us our middle value, what we're looking for. While left is less than or equal to right, we're looking for the midpoint. And this will be constant for every single thing going forward. But how this will work is, say if target nums equal to midpoint, return mid. Now, what this means is that target of nums, which means the indice at which a target is in the given array. That means if it was present. So you're given the given array, And if the indice is present, so say it was 3, if it is present, you're returning the midpoint. So it's looking through and it's finding the midpoint to be 3, returning the midpoint. But remember, because we're dealing with 2 pointers, everything is already in indices. So even if you return the midpoint, which we just set to a number, you will still be returning the indice because we're looking through the starting indice and the final indice and coming in. This brings everything into indices. So you're still returning an indice. It's telling you to return the index, right? You're still returning an index. This is still a valid answer. You don't need to do return mid of nums or anything. You can just return mid and it's a valid answer. To make this make sense, this means that if the target value is given, so for this one, the target value 5 was given, we have return mid. That means we're returning 5. But the output is not 5. Why is that? It's because when we're dealing with pointers, everything is already changed from, instead of the actual values of the array, now we're dealing with the indices. So if you return 5, you're not returning the integer 5. You're returning the indice of integer 5, which is 0, 1, 2, 2. So just like that, we'll be returning mid. It won't return mid literally, right? Because it's pointers. It'll return the indice of mid. This is also the same thing as, like, if you guys can tell, we're on the same path as binary search for now. Now, you also get into cases where you're not given it, like this, where you need to move things around to find it. So when you need to actually move left around, when you need to move right around, it's 2 pointers. So you have cases where each pointer moves in a different direction, right? So imagine L, imagine R. So imagine you're given your target is 2.5, okay? So it's here, but your right pointer is on 4, right? So this basically means that your current value 4 is greater than your midpoint of X. So you can say your target value technically you could go the other way, but okay, let's just say your target value, which is X, is less than or equal to your current value, which is numbers of mid, right? So what that would mean in code is if target is less than numbers of mid, you'll have R equals mid minus 1. Now let me change this to mid so it's more brief to understand. But you'll have this. Now you also have the case that if it is currently on the value or if it is less than the value. The only other case would be the else case, which is that it is greater than. So target is greater than numbers of mid, and then you'll do L equals mid plus 1. Oops. You don't even need to do this. You could just have it as else. L equals mid plus 1. And then you'll have a return statement, which will return, if you guys remember, it'll return L, which is what we talked about earlier. Now what return L really means is that it'll just return the indice that it would need to be inserted at, right? L, remember? You insert something and move everything backwards. But let's try to make sense of these 2 lines first, right? So imagine if the target is less than numbers of mid, okay? And numbers of mid is the value that you're currently on, right? So you're on 4, but it's less, your target is less than 4, right? That means your right would be mid minus 1. That means your right indicator is now your mid minus 1. So now it's this, okay? So now that means all of this is not included because it doesn't matter, because our target is here and we looked at here and we determined that this is still too big. R is still too big. So you're moving R. R equals mid minus 1. You're moving R. So now R is this, and you're going to keep going. This is a while loop. So you keep going. You keep going until the while loop is satisfied, while it is less than or equal to R, while it's merged at a value. while it's meeting at this junction, which is then you will return something. That return would be L. Likewise, the else value is L equals mid plus 1. It says a target is greater than numbers of mid. Imagine this, 1, 2, 3, 4, 5, right? If target is greater than, so 2.5, which is our x, is greater than a value. So we just have to put 1 for now. So think of L like this, right? And we want 2.5, which is here, x. 2.5. It's greater than, right? So L needs to move. L needs to be mid plus 1. L equals mid plus 1. Our middle was 1, but this is not it. It's too low. We need to move L to now the next indice, which is 2, but it could be anything. So we move it to the next indice. So that means anything on this side is irrelevant now. This L is gone. It's moved out of our search. So now we're at 2. Look at it again. It's still less than 2.5. Let's move it. Move it plus 1. Move it one indice to the right. Plus 1. So now this is L. Now 2 is irrelevant. And if you do the same thing in the R, you're doing mid minus 1, you'll merge. This is the part you merge at. And when you merge at this, remember, you need to return the left indice. But whenever we're at this, L will be less than or equal to right, which will also be right. So you could just return L. You could just return L, the indice that it's currently at. And this should be your solution. So if you run this, hands crossed, yes, it's accepted for the 3 given test cases. But if we go to submit it, we'll look at all of the test cases that it uses. See? And it goes through. So it passed 66 out of test cases. Runtime, it's an optimal solution. We're looking at 100%. Memory is beating 80.70%. It's beating 80%, a little bit more than all given solutions in terms of memory. So this is a very optimal solution. We're looking at an O log of n solution for search interposition.